This is Flerovium. It may not be an element you've heard of before. In fact, it's not here, or here, and here it's only in its Latin number. But here it is. It exists. Flerovium is part of group 14 elements directly below lead in period 7, which is why it was often referred to as eco-lead before it had an official name. The term indicates that flerovium is the next element to fall within the same family as lead on the periodic table. It is radioactive and only found in laboratories that synthesize it. Its name comes from the laboratory it was discovered in, the Flerovium Laboratory of Nuclear Reactions. Flerovium was discovered in 1998 by the Joint Institute for Nuclear Research in Dubna, Russia, and the Lawrence Livermore National Laboratory in California, United States. Flerovium is a synthetic element with no naturally occurring isotopes and was recorded in a lab by bombarding a plutonium ion with 5 quintillion atoms of calcium in an experiment lasting over 40 days. This research eventually resulted in a single element of flerovium. Later on, scientists found a more stable isotope of flerovium, Flerovium-289, that has a half-life of only 2.6 seconds before it undergoes alpha decay to become Copernicum. Because of this, little is known about its characteristics and properties, but it is predicted to act like a noble gas. Flerovium was predicted by a theory known as the island of stability, which states that heavy isotopes of elements may exist long enough to be studied if they contain certain magic numbers of protons and neutrons. This theory predicts that if something contains 108, 110, 114, 120, or 126 protons and 184 neutrons. For this reason, Flerovium-298, which has 114 protons and 184 neutrons, has been predicted to be the most stable isotope of flerovium, if it can ever be produced. It is often harder to synthesize heavy synthetic elements because the more positively charged protons that are packed into the nucleus, the more these protons repel each other and destabilize an atom. That is why many heavy elements are radioactive and unstable, and why elements heavier than uranium, or elements containing more than 92 protons, are unlikely to naturally occur. For reference, element 117, tennessine, only has a half-life of 50 thousandths of a second. So, why do we care? Production of an element of a more stable isotope of flerovium-298 could help solidify the island of stability theory, as flerovium-298 contains magic numbers of both protons and neutrons. This means that our view of the periodic table could just be the tip of the iceberg, and dozens of new elements may be left to discover. And while having new synthetic elements with short half-lives may not seem entirely useful on their own, their decay can also give insight into new isotopes with existing elements, like how flerovium decays into Copernicum. While elements beyond 120 protons can be predicted, and special stability is predicted for element 126, bihaxium-310, research and discovery are currently restricted by technology, mainly having a strong enough particle accelerator to bombard elements and the ability to construct heavier nuclides to serve as a target. Despite this, the research and discovery of flerovium could change the way we view the periodic table forever, and therefore is very important. The periodic table was never intended to be finished. Even when Mendeleev first drafted the periodic table's design in the 1800s, he identified gaps and was able to predict new elements based off of them. Today's scientists are no different. Trends in the periodic table allow us to predict how new elements will exist and react with their surroundings, and although they do not exist yet, that does not make it impossible for them to exist in the future. As scientists improve and develop new ways to synthesize new elements, the periodic table is bound to grow to fit them. It is no longer a question of if new elements will be discovered, but when.